Hey there, have you ever heard of geometric isomers? Let's dive into this fascinating world of molecular structures and discover what they are and how they might impact the world around us. At first glance, molecules A and B might look pretty similar. They both have two green chlorine atoms coming off the carbons, and they both have two hydrogen atoms coming off the carbons. But a keen observer would notice a crucial difference. The difference is all about where the atoms are located. You see, in some molecules with double bonds, the atoms can be on the same side. This is known as the cis configuration. Other molecules, these atoms are on the opposite side. These are said to be in the trans configuration. Trans meaning opposite. They are opposite across from each other on the molecule. Two different versions of the same molecule are called geometric isomers, and their slightly different geometric arrangement result in slightly different properties for these molecules. One thing to note is that in a alkene with a double bond, these atoms at the top cannot rotate. They are held in a fixed position. So they can't change from trans to cis. They will either be trans or they will be cis. In a single bond, we can get the molecules rotating 360 degrees. So the atoms can rotate around this middle single bond. So we can see that the chlorine here has changed position as it rotates around. Hence, they are not found in a fixed position, and we don't give them a notation as cis and trans. So this notation is only with molecules that have a double bond and will hold that groups in a fixed position. Now, these concepts aren't just abstract concepts, these differences. They actually make a big difference in everyday life. So if you were to take something like vegetable oils, here we've got some olive oil, or you could have some canola oil or sunflower oil. We have in a long oil molecule, where this long chain, every corner represents a carbon atom, we have a double bond that is positioned in a cis arrangement. So if you look at the hydrogens here, you can see it's a cis arrangement. Now, often what will happen is the oils, to make them into a solid type spread, we carry out a process called hydrogenation. Now, the problem with hydrogenation is that when we do this heating process and we add hydrogens to it, some of the molecules have their cis orientation changed to a trans orientation. Now, the trans orientation is good for those who want to have a solid spread because it increases the melting point by 45 degrees and it makes the spread last longer. The only problem is this is a trans fat, and trans fats are found to have a bigger impact on clogging arteries or causing heart disease. So there have been questions around about the processes that we use to make oils into margarine, and how can we make it so we're not making so many trans fats. Okay, so how do we recognize a geometric isomer? Well, there's two things that we are looking for when we recognize, when we want to understand whether a molecule is a geometric isomer. The first thing is it has to have a double bond, because a double bond will stop the atoms or molecules on either side from rotating and hold them in a fixed position. The second thing you need to have is on either carbon, the carbon on either side of this double bond, you must have two distinct groups. And on the a left-hand molecule, we've got a CH3 and an H, which is two distinct groups on the left, and a CH3 and an H on the right. Now, we can name this not butene, as we would think, but because it's in the cis arrangement, we call it cis-butene. And the same is true for this trans example on the right. This is butene, but because it has the substituents, the groups or atoms coming off the carbons of the double bond, in a trans arrangement, we call it trans-butene. And notice I've missed the 2 out there. Let's look more closely on how we would identify whether a molecule is a cis or trans geometric isomer. So remember, the first thing I said is we had to look and see if it has a double bond. So notice this molecule on the left does indeed have a double bond. And then we look specifically at each side of the double bond. So I'm looking at the carbon on the left. So what are the 2 groups or atoms that are coming off that carbon? So the first one we can see here is a CH3 group, or a methyl group. We can also see a chloro group coming off. So this meets the second requirement, is that there are 2 different groups coming off one of the carbons. But we need to now make sure there are 2 different groups coming off the other carbon, which there is, because here we have an ethyl group coming off this carbon, and we have a chloro group. And these 2 groups on the right are different than each other, just like the 2 groups on the left are different to each other. And we have a double bond. So this is a geometric isomer. We can see that the chloro groups are arranged across the double bond. So this is a trans. So trans 2,3-dichloropentene. The molecule on the right, exactly the same. This is just the other version of this. It's got a double bond. It's got 2 different substituents. That's another name we can use for groups or atoms on the left, and 2 different substituents on the right. That makes this also geometric isomer. These are actually 2 isomers of 2 of the same isomers of the same molecule, 2 geometric isomers, the trans and the cis version. So let's have a look at a couple of examples again on this next slide. Okay, let's look at 3 different molecules, and I want us to look and see whether they can have geometric isomers, whether they can have a cis and a trans isomer, and we're going to use the rules that we looked at the previous slide. Okay, do they have a double bond, or do they have 2 different groups of substituents coming off each carbon of our double bond? What I'd like you to do, just pause the video, have a go at identifying these yourself, and when you're ready to go, start it again. Okay, welcome back. Let's just go over this and see which ones of these can be geometric isomers. So the first one has a double bond. It meets the first requirement. On the left carbon, it has 2 different substituents, a CH3 or a methyl group, and a hydrogen atom. So that meets the requirements on that part. And on the right hand carbon, it has a hydrogen and an ethyl group, a C2H5. So yes, this meets both requirements. We can see the hydrogens are across from each other. So yes, this can have geometric isomers, and this is one of them. This is the trans isomer. Let's look at this next one. So yes, it does have a double bond, but look at the 2 groups that come off the carbon. Sometimes this can confuse you, because we can see that the group on the left here is a CH3 group, but it's drawn in an expanded form. That is, we can see the bonds of the hydrogens, where the one on the top is drawn in a condensed form. However, they are both CH3 groups, so they are not different groups or atoms coming off this carbon. So this will not meet the requirement, even though the groups on the right hand side are different. So no, this has the same groups on this left hand carbon, so it cannot have geometric isomers. Let's come down and have a look at this one. Now this is an interesting one. It does have a double bond, but note, it does, if we go into, we look at it, we can't see 2 groups that are similar across the molecule. But that doesn't matter. We just want to know, can it have geometric isomers? So we follow the rule. On the left hand side, does it have 2 different groups? Well, yes it does. it has a CH3, and it has a chlorine group. On the right, does it? Yes, it does. It has a hydrogen and it has an ethyl group. So yes, it will have geometric isomers. There will be two different versions. And just because of the way this chlorine and the hydrogen are placed, I would call this a trans. Last one. So we can notice on the last one that yes, we do have two different groups that appear to be across the molecule from each other. However, the bond that's in between them is a single bond. So that means that these bonds here are able to rotate about the single bond. So they are not held in a fixed position. So at any other time, they could be at the top next to each other in a cis arrangement. So because they're not held in a fixed position, this is not a geometric isomer, and it's not held in a fixed position because it doesn't have a double bond. Okay, so geometric isomers, though small in difference, they only have a very small difference on how they're arranged, have actually very different chemical and physical properties. Now the reason that happens is because let's look at this one, this cis-butene on the left here. It actually has a boiling point of 58 degrees. It's polar. Now the reason it's polar is it's got these chlorine on one side, so it's slightly negative on one side and it's slightly positive on the other. And because of its polarity, it's slightly soluble in water. So it's going to behave in different ways if it's in living organisms or if it's reacting with chemicals because of these properties. The trans-butene on the right, because it has these electronegative chlorine atoms symmetrically across the center of the molecule, it's going to be nonpolar. And it's actually got a boiling point that is lower because of basically because it's nonpolar, and it's going to be insoluble in water. No, it doesn't dissolve in water even a little bit. So our polar one, our cis, has got slightly different properties than our trans. So it makes a big difference, this positioning, and it's really important that we find out how we can determine whether something is a cis or a trans geometric isomer. So next time you come across a molecule, remember that their tiny structural changes can lead to big differences. Thanks for watching. If you found this interesting, give it a thumbs up and subscribe for more science insights.